Welcome back everyone. We'll resume our lectures on nonlinear and adaptive control. In this piece of the lecture, we'll talk about the basic idea of model reference adaptive control, and then we will introduce the MIT rule as a technique for implementing a version of model reference adaptive control. The basic idea is you would have a reference model with some set point as an input, and of course that reference model would produce the desired output. Down here we have the normal control loop of a plant where the output of the controller U is an input to the plant, the output of the plant is Y, and this is taken as a negative feedback signal to the controller. Another input to the controller would be the set point. Now, our purpose is to make the relation between the set point, call the set point say UC, and the output of the real system similar to the relation between UC and the desired output of the reference model. I'm going to call that say YM. In order to achieve this, I take measurements from the output of the real system, the control signal, and the output of the reference model. These three signals will go through the adjustment mechanism, and the purpose of the adjustment mechanism is to tune the controller. So here tuning, such that the relation between the output of the actual system would actually be similar to the output of the desired output. And if we do that, we achieve what's called perfect matching or model following. The plant is assumed to be unknown. Specifically, we assume the parameters to be appearing linearly in the equation of the plant, and these parameters to be unknown. The reference model is normally designed according to specifications. However, of course, constraints and limitations could be applied to the reference model. The requirement is that the output of the real system would follow the output of the reference model. And of course, if we achieve that, we will reach perfect model following. Otherwise, a small error could happen in some designs. We have to have a structure for the controller. So if we assume a single input, single output system with output Y and input U, the most general control structure for such a system would be a feedback component. I'm going to call that feedback component S over R, and assume here a negative feedback. And a feed-forward component, I'm going to call that component T over R. And here you have the set point UC. Now, T, R, and S are polynomials. In P, which is d by dt. So if you like to write an expression for U, I would write U equals T over R times UC minus S over R times Y. Now, the problem is to design T, R, and S such that the relation between Y and UC would be similar to the relation between the desired output and the set point UC for the reference model. In order to achieve that, we need some adjustment mechanism, and we are going to look at two of them. The first one is the MIT rule, And the second one is a Lyapunov based design. Maybe we mentioned before that the MIT rule does not guarantee stability. That's why it's not really used nowadays. However, the Lyapunov based design would ensure the stability of the closed loop system. Okay, let's start by the MIT rule as we agreed before. If we assume that the error is the difference between the output of the system and the output of the reference model, and the parameter of the controller to be adjusted, we will call that theta. Like for example, if you take u equals some constant t node times the set point minus another constant times the output, then theta would be either t node or s node. So that's what we mean by the parameter theta to be adjusted. So the adjustment mechanism will be responsible for adjusting t node and s node such that the desired output would be achieved. Now, in order to do that through the MIT rule, we assume an index. That index is called j, and it's 1/2 the error squared. The idea is to adjust theta such that j is minimized. We do that by changing theta in the negative direction of the gradient of the index. That's why the MIT rule is d theta by dt. The rate of change of the parameters to be tuned is equal to minus some constant gamma times the gradient of j with respect to theta. The negative gradient of j with respect to theta. Gamma, as I said, is the gradient, the adaptation gain. This is a constant that is normally chosen by the designer. Actually, it affects the performance of the controller. However, there is no analytical relation that would tell you how to choose gamma. So it is based on experience or based on simulation studies and experimentations and so on. Now, j is 1/2 e squared. So partial j partial theta is actually e partial theta. That's why we can write the MIT rule as minus gamma times e partial theta, and this derivative is called the sensitivity derivative. Okay. The basic assumption in implementing the MIT rule, and maybe most of the adaptive control techniques, is to assume that the variation in the true process parameters is much slower than the process variables. That means that the unknown parameters, the actual unknown parameters of the plant, almost don't vary with as compared to the change, say, in the output or the state variables of the system. So this is a basic assumption for the coming analysis. As an example to the application of the MIT rule, we are going to start first by a simple example of adjusting a gain, a feed-forward gain. So I'm assuming here a process that has the relation y equals k times a certain transfer function g of s times the input. We are assuming here that the transfer function is known, while the gain is unknown. So our purpose here is to track a certain system. So if I assume the reference model to be given by k node times g of s times a set point u of c. So my purpose here is to select a controller, a gain controller, and adjust the parameter theta in that controller so that the output of the system y would follow the output of the reference model by just adjusting theta. So in order to proceed, I'm going to define the error as the difference between the output of the system and the output of the reference model. So if I substitute here for y, it would be k times g of s times u minus k node times g of s times the set point. Now in order to calculate the partial derivative of a with respect to theta, then I have to substitute for u here by its expression, which is theta times uc. So the partial derivative here would be k times g of s times u3, and of course the derivative of the second term here would be 0 because theta doesn't appear. So if you do that, we can look to the original equation of the reference model and substitute for the term g times uc by ym over k node. So this would be k over k node times ym. And consequently, I can write d theta by dt as minus gamma e, the partial derivative of e with respect to theta, and that would be k over k node ym. Now I can combine these constants together in one constant. So I will call that gamma, say, bar, and that would be e times ym. However, this assumes that at least I have to know the sign of the unknown parameter k. So I'm assuming here k is just greater than 0. It's a positive number. This is just an assumption. So it's unknown but constant and positive. So if I do that, I will be able now to actually draw a block diagram that implements this controller. So let's try to do this. Suppose that you have here this set point and the output of the reference model. I would like to form the error. So I take the difference between the output of the process and the output of the model. This would be the error signal. And then I have to multiply that error signal by ym. So here is the multiplication of the error signal times the output of the reference model. And the result of that should be integrated. So I multiply here by minus gamma bar over s. 1 over s is the integrator. And the result of that would be theta. So what I have here is as an input an expression for theta dot, or d theta by dt, and then the integration of that would give me theta, and this value of theta should be multiplied by the set point in order to produce the actual value of the control signal. So this is a block diagram that illustrates how to implement a model reference adaptive controller for a special case when you have an unknown gain. As a second example to illustrate the implementation of the MIT rule, I'm going to consider a first order system, dy by dt equals minus a y of t plus b u of t. And of course here a and b are not known. The reference model is another first order model, dym by dt equals minus am ym t plus bm uc of t. The constants am and bm are selected so that the trajectory ym would behave the way that we like given the set point uc. The basic assumptions here are that a and b are unknown, while the sign of b is known, and I'm going to assume it to be positive for simplicity. The control law would be a usual control expression that contains a feed-forward term depending on the set point and another feedback term depending on the output measurement. If we define the operator p as d by dt, I can write the equation of the closed loop system. This is just by substituting this expression for u into the equation of the plant dy by dt. So that's what I'm going to write here. So I would write p y equals minus a times y plus b times the expression for the control t node uc minus s node y. Now I can bring all terms that contain y into the left hand side of the equation, so that will be p plus a plus bs node times y of t equals bt node uc. This is the closed loop equation of the system. Now I can use this equation to calculate the error equation. The error equation would be y, which is bt node, times uc divided by p plus a plus b s node minus the expression for the output equation ym, and that would be bm divided by p plus am times uc. Now once I get the error equation, I can calculate the sensitivity derivatives, and that's to take the derivative of e with respect to t node and s node. Of course the second term here is not a function of t node or s node, so its derivative with respect to any of them will be 0. So if I take the derivative, the partial derivative of e with respect to t node, I get p uc divided by p plus a plus bs node, and I repeat that with respect to t to s node, so that will be p squared times t node uc, and this is divided by p plus A plus B S node all squared. Now we have derived the equation for the closed loop system, and can write the relation between y and UC in this form. And I'm going to use that to simplify the equation of the sensitivity derivative with respect to S node. So I will just take BT node UC divided by P plus A plus BS node and replace that by Y. So I can write this equation as minus B times Y divided by P plus A plus B S node. So this is the equation for the sensitivity derivative for S node. Now I'm having a trouble here because these sensitivity derivatives cannot really be calculated or implemented, since A and B, which appear here and appear also in the equation of T node here and here, these are not known. So I can't really implement these sensitivity derivatives in real time. So I'm going to assume that once the system converge, the closed loop poles of the system will be actually the closed loop poles of the reference model, and that means that this denominator can be replaced by P plus AM. So if that's true, then I can write the sensitivity derivatives with respect to T node as B over P plus AM UC, and the sensitivity derivative with respect to S node as minus B Y over P plus AM. And finally, I can calculate the rate of change of the parameters, the adaptation equations for the parameters. So just by substituting for dE by dt node from the equation here, I can write that as minus gamma E P times UC divided by P plus AM. So this is the first equation. And the second equation would be, I'll substitute for dE by dS node from here, from the sensitivity derivative of that. So that will be plus gamma E P Y divided by P plus A. So I notice here that I have a product of gamma times B in both expressions. B is not known, however its sign is known. So I can replace that product by another constant, I call that gamma dash. So these two will be just gamma dash. And that completes the solution. What I can do now, I can write the equations for the adaptive law as dt node by dt equals minus gamma dash E 1 over P plus AM times UC, and ds node by dt as gamma dash E 1 over P plus AM times Y, and the control law U T node UC minus S node Y. So this is the complete set of equations that can be used to implement the required adaptive control.